Hello. So sorry for that. Hello, thanks for coming speaking about Docker and the new release 1.12. Can you hear me fine? Good? Good. Thanks. So some things about myself. I'm Antonis. I'm from Athens, Greece, so pretty near here. We're all Balkans. I'm also a Docker captain, which is a program from Docker with individuals who like to share things with the community. And I'm a user of Docker since version 0.6, so I've seen Docker in many different phases, from a not-so-stable project to a very nice and robust project that is today. I usually code in Python, but I've used many different languages. We use Django, which is a Python framework for our company, and I'm leading the technology at a company called Sourceler. At Sourceler, we're utilizing Docker in order to create developer environments in the cloud. In general, I like automating stuff. We were discussing before with a friend here of how we don't want UIs and clean stuff, and we want to automate everything. I like to talk about DevOps, containers, and how you could optimize your development workflow, because developers need to have a good workflow in order to work faster and safer. Let's see what we'll discuss today. So we'll start with how Docker started as a project. We'll set some history, and I'll also share my personal experience of how I started using Docker in my company. Then we'll start seeing the anatomy of Docker. We'll start from the engine, which is the core part of Docker. We'll see how the engine has many different components and how these components interact with each other. And then we'll start seeing the ecosystem around the engine, which Docker created. And finally, we'll start going to the orchestration part. We'll start with the legacy Docker Swarm product, which is now developed still, but not really the best way to go. And then we will make an introduction to SwarmKit, which is a library created by Docker for orchestration, which is now embedded inside the engine. We'll talk about services, dub files, which are the new things coming with this release. And of course, at the end, we'll have demo time, so hopefully everything will go nicely. So before we start, I'd like to do some hand waving so you all get warm up and everything. So who has used at least once Docker in his life? Maybe just simple Docker run, so almost everyone in the room. So from you, who is using Docker for something in his daily life, like maybe either production or testing or, I don't know, development? So about 1/4, 1/5 of the room. And who is using Docker in production? Like you have Docker either through an orchestrator like Kubernetes, for example, or Mesos, or Docker Swarm. So very few people. So that's a nice thing, because Docker started as a development tool, and now you see Docker in production, but this transition is slow, and we'll see how you can make this transition faster throughout the presentation. But OK, let's start from the beginning. Docker was a project which was first time introduced by Solomon Hykes, the CTO of Docker now, at PyCon at 2003, if I remember correctly. And back then, Solomon went up the stage and said, OK, I have a sprint talk. I'll do a quick presentation of a tool we have created at .cloud, was a company back then. And he started by opening a terminal and running a simple command, docker run base echo hello world. This is a simple command that just prints out hello world. Not everyone was very impressed by that, because they could not understand what happened under the hood. And then he started explaining that, when I did this, then a new process was started. This process was isolated using C groups for resources and also namespaces for the view of the system, like network and for example. And then I had a custom file system, which was Ubuntu at the presentation, attached to the process, and the process ran. So everyone was amazed, and everyone started talking about Docker. This was the presentation we also watched at Sourceler, and we said, OK, this is something that seems interesting. And back then at Sourceler, we just had a simple web UI where you could just throw some code, C code, for example. You would hit the run button. This code would go to our backend. It would get compiled. It would run. And then we would return the result to the front, to the user. But when we started using Docker, and we did some quick tests, we would have a complete terminal where the user could interactively add, for example, something in the input, or it could she could easily hit Control-C and stop the process and everything. So Docker was a real game changer for us. And then we started utilizing Docker to start building a complete developer environment where you can build Python, Node.js applications. You can have database attached to it, and you can do this all through a web UI. So let's start by seeing the anatomy of Docker as a component, the anatomy of the Docker engine. Sorry for a second. OK, so the Docker engine is actually the core piece of Docker. It's the one that runs containers for you, manages them for you, and you can also talk to it in order to instruct it to do some things for you. And actually, the structure is something like this. So you have at the center something called the Docker daemon, which is a daemon that's running all the time in your system and knows how to run containers. Then on top, you have a RESTful API, which is the one that you interact remotely with the engine. So for example, I don't have to be in the same machine that Docker runs in order to be able to run containers. I can be in another machine and just instruct what I want to run through a RESTful API. And on top of that, also, there is a Docker CLI, the client, which is, actually implements this API, calls it, and runs things for you. With this simple stack, you can also manage data volumes. You can manage networks. You can also manage, of course, containers and images, which images are actually the file system that your container runs in. So I can be in an Ubuntu system, for example, and run a CentOS or an Alpine container without needing to do anything. Just download an image and run it. This makes it really easy and fast. But let's dig a bit deeper inside the engine and the daemon itself. So there are three core components there. The first one is run C. So when Docker started, it had everything bundled inside. But then they decided to create a run C, which is a project now adopted by the OCI, the Open Containers Initiative, which helps you run containers in a specific, with a specific API. So for example, if I just want to run a container, I don't have to use the complete Docker stack with everything included. I can just use the run C, which is open source also, and then start running containers without doing anything with the images and attaching volumes and everything. On top of this, there's the Docker daemon. So what does the Docker daemon do? Docker daemon has an overview of the containers that are running in the system at a given point. So for example, I can ask Docker and say, how many containers are running? And Docker will reply, you have 5 containers running. You have another 5 containers that have exited with exit code X or whatever. And also Docker has all this RESTful API that we talked about before, where you can talk to Docker and say, use run C, which is a system tool, and run this container for me. So Docker will do it. Also, Docker has some other nice things to do, like, OK, if this container stops, then I want you to restart it, for example. Or if it stops with next code other than 0. And of course, the Docker client, which is not so special, but it's a very handy tool in order to use Docker from your terminal, because Docker without the Docker client would be just an API. You needed a way to access it easily. But Docker is not so important just because it's a very good runtime, because this is only the runtime of Docker. But also Docker has invested a lot in the ecosystem, and the ecosystem is the one that drives Docker forward. So Docker does not want to be just a runtime system. At Docker, they want to create tools of mass innovation. So this is a goal that they have. This is their mission. And this needs, by default, to have a very good ecosystem around it. So Docker had a very clean API. It has supported versions of the API, so you can keep using a version even if Docker goes to a future release. And then this allows you to create, for example, things in these areas. At start, you have orchestrators. You might use Docker, but you might not know that you're using Docker. Victor, for example, in the presentation said that in Mesos, people do not know they're using Docker, but under the hood, Mesos does not orchestrate only VMs, it also orchestrates containers. So you can use Docker without knowing it. Also, Kubernetes is based completely on Docker. I think they have created a version now that also supports Rocket, the other container runtime, but Docker was built around Docker. And also you have Nomad, which is from HashiCorp, where you can orchestrate containers, VM, or whatever you need. Then these are the tools that are using Docker as it is. There's also the plugins ecosystem, where you can put custom logic and give superpowers to the engine, for example. This is done with volumes. This is done with networks. So if I don't like Docker's implementation of volumes, I can create my own volume driver, for example, and attach volumes the way I want them to attach. Also, there are authorization plugins which are active now, and there's authentication plugins which are trying to be released and hopefully will be released soon. Then you have also several tools that help you know the state of your cluster. For example, you have cAdvisor, which was created by Google, or Prometheus, where you can easily have an overview of the cluster, how many containers are running, which containers are there, and everything. By the way, I forgot to mention it, but if I go too fast or you want to ask any questions, you can also do it throughout the presentation. We'll have a Q&A afterwards, but just stop me, raise your hand, and if needed, I'll repeat the question for the video. So a very nice and notable tool that did not start within Docker, but was a very interesting project, and in my own opinion, moved the project forward, was Docker Compose. So let's say that I have Docker. Okay, so I can just start running containers one by one. Docker does it for me, does it in a good way, and I'm sure that if I instruct Docker to run a container for me, this container will run in a good way. But then, what if I want to run a Django project, for example? In Django, which is a Python framework, as I told you before, I can run web applications, but I need maybe something for casting, so I need Redis. Maybe I need a database to store my data, so I need the Postgres database. And I want all these pieces to be interconnected and know how to talk to each other. So Docker Compose does exactly that. In Docker Compose, you have a clear definition of how things should run. So the correct command, the correct image, the environment, volumes attached, and everything. You might have a network, or you can have links in order to connect pieces with each other. And then you can just run a simple command in Docker Compose, which is called Docker Compose app, which will start all the services for you and make sure that they are started in a good way. So Docker Compose was a pioneer in the orchestration part, in my opinion, because Docker Compose was the first try from the community to create a clear picture and a clear definition of how you run things using containers. So Docker Compose started being used for development. So for example, in my local machine, if I wanted to run something on Docker, I would use Docker Compose. But when you went to production systems, there was a very critical problem. Docker Compose was talking the Docker API, and I could easily run containers in one server. But usually you don't have just one server in your production infrastructure, you have many of them. And you cannot just go one by one and say, you know, server 3, I want you to run this. Server 5, I want you to run the other thing. And do that kind of stuff, because this is not viable at all. You have to treat your machines like cattle and not like pets. So you have to be really distributed. So Docker Compose was a nice way to describe things, but they needed a way to orchestrate things. And here comes Docker Swarm. So the core value of Docker Swarm was, you know, we have a nice API with Docker. We have a very nice tool that uses the Docker API in order to orchestrate containers, which is Docker Compose. And we want to create a way which has the same API, but at the same time can talk to many machines. This is actually the logo of Docker Compose. And let's see a bit how the first architecture of Docker Swarm started. So I have one or more Docker Swarm masters. These masters are talking to a KV store in order to retain consensus and know the state of the cluster. This could be either Zookeeper console, etcd, or any other thing that was implemented in libkv, which is a library to talking to these KV stores. And then the Swarm cluster knew how many machines were below them, and start saying, okay, you know, you want to run this container, and then I see some space in server 3, you'll go there. So the whole orchestration part started evolving and started getting some traction. Also, there was a very simple API, because Docker API was already defined. So all the tools that work for one Docker server could now start working for multiple Docker servers. They also created a simple way to define constraints. So for example, let's say that I have a server which has an SSD disk, and I want to run something that is disk I/O intensive. I don't want this to land in the other 4 servers, for example, that have slow disks. I want to land it to the correct server. With a simple labeling on the nodes, for example, you could make Docker Swarm orchestrate and make sure that the container lands to the correct server. The problems that started appearing when such solution was introduced were two. The first one was networking. When you have all the containers running in one host, it's really easy to handle networking for Docker, because the only thing Docker would do is route the request throughout the containers that were running in the same system. If you don't know how things work in Docker, well, actually, there's a virtual Ethernet for each container, and this virtual Ethernet is bridged to a Docker bridge. Then, since it's bridged there, every packet that comes either outside of the container or inside from a container passes through this bridge, so Docker could do the routing for the containers. But when you start having multiple machines, you need a way to route the packets to other machines throughout the cluster. So Docker started with a plugin called Overlay Networking, which was by default inside the Docker engine, and also created a simple API and model in order to create more plugins like this one. So there were many plugins that started from there, which was, for example, Calico or Weave and other nice companies which created plugins implementing this model. This model is also open source and is also available in the OCI. The other serious problem that started appearing when Docker started talking to many machines were the volumes. So if I'm in a server and I have a volume, then I can easily take this volume and move it between containers. Let's say I want container A, then I take it from container A and put it in container B. And it's really easy, it's just mounting local directories. But when you have data in server A that needs to be accessed by a container that is scheduled in server B, then what do you do? Docker did not have a solution out of the box for this one, but also created volume plugins. So volume plugins were really easy and pluggable. So you could easily pick a plugin that implements the API and put it in your cluster. And then this plugin would take care of whatever use case you might have. For example, there are plugins that talk to block storage. So for example, if I'm using AWS and I have a block storage device attached to server A, and I want it to be attached to server B, I can easily use a plugin that does this for me, and Docker will say, okay, you know, this volume is not needed now in server A, it's needed in server B. Then the block storage would change to the other server, and it would be mounted to the correct container. So with this, it would be really easy to start and have this logic of, you know, having multiple servers with the data in a block storage, for example, or you could have ZFS volumes, which were copied on demand. So if I start in server A and I want to run server B, I could easily copy the data, and this logic was implemented by the plugin. It was not something that was very strict by Docker. All these things went a nice way, and it was really nice to see people implementing Docker Swarm. And are there any Docker Swarm users here? One? Okay. Okay, so you will not be disappointed that Docker Swarm changed. I know Victor will change, So Docker said, okay, the Docker API was created for a specific reason in order to be able to run containers in one server. And Docker Swarm was a very nice proof of concept of having this logic be implemented to a cluster. But the API was not ready for this. I mean, the API was designed for a different purpose. So they decided to create a new product called the Docker Swarm Mode. So with Docker Swarm Mode, you get Docker native orchestration. It's really nice. It was built through a library called SwarmKit, as we said in the start. And this library was there to make the whole orchestration part. There are some new key concepts introduced in Docker Swarm Mode. And let's see them so we can talk about them. The first key concept that did not exist in the Docker API was nodes. In a Docker server, you don't need to have the meaning of nodes. Nodes are meant for a cluster. So Docker Swarm introduces this new key concept. So for example, if I have a Docker Swarm cluster now, I can easily do Docker node ls, and it will return all the nodes being part of the cluster. The second very important change was the services. Services are a way to define what you want to run in the cluster and not being tightly coupled with containers. So you define something in services, and then services are translated to tasks. So I create a service which has some replication, for example, of 3, and then 3 tasks will spawn from this service, and will run throughout the cluster. The last thing that was really important in the design of Docker Swarm was the orchestration, which means that orchestration is built in. But let's see what changes does this introduce to the Docker engine. So the first and most important thing in this change is that the Docker engine is 100% compatible with the previous versions. If you do not enable this mode, then you can use the Docker engine the same way you did before. You don't have to do anything or nothing special. The things that are introduced is actually the notion of managers and workers. So the engine runs either as a manager or as a worker in the cluster. Then there's TLS enabled by default, so all the nodes talk to each other through a TLS connection, and it's all secure and safe. There's a certificate authority that is there so that more servers can join in and certificates are created for them. And there's the load balancing, service discovery, and distributed key store. But let's see a bit the architecture of this new, the topology of this new architecture. First of all, on the top, you can see the managers. So the managers are the ones that are the leaders in the cluster. They decide which runs where, they have consensus with each other, and as you can see, the distributed state store is not something that is external like it was in the previous version of Swarm, but is integrated inside the cluster. So these servers talk the Raft protocol, which is a gossip protocol also implemented by etcd, for example. And they can have consensus, and you can send instructions to any of the managers that you want, and then the leader will be asked, and the correct action will be taken. Then you can easily have as many workers in the cluster as you wish, and these workers will take the load. You can either decide to run containers in the managers or just run containers in the workers. A nice thing that you can do with this is that you can easily scale up the cluster or scale down the cluster. You can just add nodes, and these nodes will connect to the masters. Will say, oh, I'm here, and I'm a worker, and I'm at your service. And then the managers will start dispatching load to these new servers. The other nice thing is that since this is completely decentralized, you don't have a single source of failure like you might have in previous versions of Swarm. And as we discussed before, this is secure by default. So all the connections between workers, managers, the managers themselves, and the whole networking infrastructure, which makes sure there's routing between containers inside the cluster, this is all done through a TLS connection. Let's see the most important part that this new topology introduces, which were services. As we said before, services are the way of defining what you want to run in a cluster. So I can easily define a service, say that this service, for example, will be replicated. So I want to run at all times 3 replicas, which will run 3 containers, for example, in this case. Or I can do another strategy. For example, I can say this service is global. Global will start and make sure that one service is running to each of the nodes. So, for example, if I want to have something that has access to the system itself for data logging, for example, I can easily create a global service and make this service run to every node in the cluster. Also, services define deploy and restart policies. So you can say that if a service gets killed, for example, then restart it, or maybe postpone restarting it and start it after 5 seconds, for example. And also you can define rolling updates, because you can say that if a service needs to be updated, then start killing services, replacing them, and then continue until you finish with all the services. When a service runs, it actually creates tasks. Tasks are the way you have in the Docker Swarm cluster to run containers. So tasks are one-to-one mapped to containers in the current implementation. And when you start one service with a replica of 3, then 3 tasks get created. When a task finishes, either because it, for example, exits with a bad exit code or exits with 0, then a new task is created. So you don't have to take care of tasks and do everything you need. Creating services is pretty simple, and if you have used Docker, it will remind you the way you run containers. So you have a Docker service create, then you put there some options, and then after putting the options, you get the image, like you would do in a Docker container, and the arguments that need to run in this service. The other interesting thing that is introduced in the latest version of Docker Swarm is distributed application bundles. This feature is not stable, it's experimental, but it's a very nice way to describe what you want to run in the cluster. So again, if you have multiple services that need to run and interconnect with each other, then this starts to get a bit messy because you have to start all the services from scratch. You have to know how to connect services with each other and all that kind of thing that you had in containers. So distributed application bundles is to services what Docker Compose was to containers. So it's a way to have more than one services created from a specific file, and you can also make sure that you know all the services run the correct way. The very important thing in Docker distributed application bundles, is that you can have a very specific definition of which image you want to run. So in this case, you don't just run an image with a tag like you would do in Docker, which would be latest, for example, and not be sure that this tag is correct, but you have the exact checksum of the image. So if you, for example, have your CI tool build the image, then you are sure that the same image that passed all the tests is the same one that runs on your production cluster, which is very important to make sure that your production cluster runs as you wish. Also, since DAB files are managing services, it's really easy to have rolling updates and all that kind of stuff that were introduced in services. I would like to also, OK, this is the command that you deploy a DAB file. So you just do docker deploy and then the stack that you wish to deploy. If the stack is an update of a previous stack, then only the changes will be deployed to the cluster. And also, there's a very nice tool that helps you manage all these stacks called Wellprint. So you can have it and look it up on GitHub if you'd like to learn more about how you can manage all these DAB files. There are also some extensions inside the Wellprint project that help you better orchestrate these things. So that's with the talking, and now it's time for the interesting part, which is the demo. Do you have any questions up to here, or would you like to gather all questions at the end? I am either pretty good or pretty bad, because no questions is not a good sign usually. Anyway, let me jump in the demo. Let me mirror this place. OK, so can you see the screen at the back? Do you want? OK, it's OK. You don't want larger letters. OK. So I have created a simple cluster in Azure. I have not enabled the Docker Swarm, but I have created all the machines in order to do the demo faster. You will get the repo afterwards, and all the instructions for creating the cluster are there. So let's start with initializing the cluster. The first thing that I need to do, as you can see, is I want to start connecting to the first machine, which will be the manager for the example. And then I will just run a simple command, which is called docker swarm init. I'm going to paste. Oops. I think that copy pasting is not working. Let's try this. OK, so the first command will enable the first machine in my local Docker client, and the second command will just initialize the cluster. So it's just a simple and quick command. And then, as you can see, I have a token which I can use in order to join more nodes into the cluster. What I'm going to do is just expose this token to an environment variable so I can use it later on more easily. And I will also export the IP of the master so that I can in future commands. Nothing special until now. Now, as you can see, I have two more machines called Vox1 and Vox2. These two machines will be the worker of the cluster, the workers of the cluster. And I'm going to just copy and paste this command here, who will just SSH to each machine of these, and will join with a given token and a given IP of the master. This should be pretty fast. As you can see, all this process is pretty straightforward. I did nothing, and I have a complete swarm cluster now running. with just 3 simple commands, and this cluster is secure by default because there were certificates created by the master. These certificates were created also for the worker nodes as they joined. I have a secure token in order to make sure that the workers join the correct cluster and everything. I knew nothing about it, I did nothing about it, and still it worked very easily. The next thing I'm going to do is create a new network. As you can see, I'm using the driver called overlay, which is the multi-host networking of Docker Swarm mode. And then I'm creating a new service, which I'll name it Flask host name. It's a simple Flask application that just returns the host name of the server it's running. And I will make sure that this is joined to the network that I just created. And the port 5000, which is the port that the service is listening, is mapped to the port 30,303. Also, the image is public, so you can run this easily afterwards. So what did I just do? The first thing I did was create the network, and the second thing, also publish the port. The interesting thing about Docker Swarm is that this published port is available to all the nodes in the cluster. I don't have to go to the correct node in the cluster and hit this port in order to access the service, but I can hit whichever node I want, and the request will be routed to the server that the container is actually running. So let's test this. I have no idea where this landed, so I'm just going to use the first machine, the manager, and I will do a simple while true do curl. So as you can see, the host name of the container that the service is running is this one here. What I'm going to do now is use a command called scale. So what I want is to start, I have just one replica here now for the service, and I want to have 5 replicas. So I'm just going to copy and paste this here. Where is the cursor? And then I'm going to run the same command again. As you can see, I continue hitting just one server, but the request is going to be dispatched to 5 different containers throughout the cluster. So load balancing is integrated inside the Docker Swarm, and I can easily hit every container I want from any machine I want. So I don't need to know anything about the state of the cluster. I just need to know which port I need to hit, and this port will route me throughout the cluster in a good way. For the example, I will also go back to just one replica, and you'll see still having many containers running, but after some time you'll see that this will stop in the same container ID. So as you can see, it continued routing the request to the whole cluster, and now that every other replica is shut down, I only have one replica running. But that's not perfect, so we'll just start having let's create, a new load balancer. So Sirix is a load balancer that we have created. It's open source, so you can find the code online. And this load balancer makes all the definition of the routing in a Redis backend. So I can easily dynamically create routes for Sirix. So the first thing I'm going to do is use Docker Compose, because in the repo here, let me find it, I have a Sirix.yaml file, which is a Docker Compose file. This Docker Compose file defines all the services that Sirix needs in order to operate. So I have the proxy image, which does all the proxying. It's based on Nginx. Then I have the API layer, which is the API listening through a RESTful API for new routes to be registered. And then there's Redis, which is actually the component that is all the data is stored. Then, as you can see here, I have the service that I had just created and the image that I used before. So the first thing I'm going to do is do a Docker pull. This will pull the images to all the node I'm directed to. And after it does that, just give it a second to finish. I'm going to use the command called bundle. So I'm using the same Docker Compose file that I used before, which is called sirix.yaml. And then I'm using the command bundle, and I say, OK, I want the output file to be vox.dub. This creates a file here, which is actually the definition of the cluster that I want to create. So it has all the environment that was taken from the Docker Compose. It has all the services that we had print in the Docker Compose file and everything. With another simple command, I'm going to deploy this to the cluster. So Docker deploy voxt, which is the name of the stack that I just created, creates a new network for this stack alone. It also creates the services that need to be created for this stack. And all the services are now running in the cluster. But I just said, so let's see it's actually working. This is a simple command to expose the port of the proxy. The proxy exposed the port in a port like we did before in the cluster. And with this command, I'm going to expose it in an environment variable. And now I'm just going to do the same command that I did before for the Flask service. But this time, I'm going to hit the port of the proxy inside the 0 node in the cluster. And it's not working. OK, let's see what I did wrong here. OK, something's wrong with... I think I'll switch to describing what should happen here. Maybe I have some syntax error in my code. But what I did here was to start hitting the proxy service. And the proxy service would just return the default page because we have not inputted any routes inside the proxy. After we did this, then we would move on and create some routes inside the proxy. And after doing so, then we could see that these routes were respected. But I think I have something wrong here. One last try. It's not working. So we could easily have a complete stack deployed. This is still experimental, so there might be a problem with the cluster, or most possibly there's a problem with my code. And that's about the demo. Sorry, you did not see the final outcome, but I will not do live debugging here. I think live demo was quite enough for me. Oops. So thanks a lot for being here. I hope you have a better understanding of how a Docker Swarm cluster operates. And I'm open for questions or whatever you need to say. No questions? One question. Just a moment for the mic.
Where are the logs for Docker Swarm engine? For example, when it's killing the services or things like that, when something goes wrong.
OK, let me just switch back to here. So I
can... Maybe to investigate what's wrong now.
Yeah, I mean, yeah, but I will not do the most probable thing is that I have exposed the wrong port. But I'll check it later and I will update the repo.
I would like to see in logs something like that. It's wrong port or something like that. How to debug when it's not working.
So that's what I'm going to do now. So I'm going to do Docker service, and then I'm going to input the service that I want, which is voxt proxy, for example. And then I'm going to do, oops, PS. So the first thing that I want to know here is that my service is running. So this says that, it's actually running, so it's not your fault. Then there's a command called docker logs. But I think this command is not working now for tasks. So if the task, this is actually the task ID that I took here. But I don't have the latest version of the engine installed locally. So the client does not know how to instruct the server to show the logs of the task. This could be the next debugging move, and unfortunately it's not ready. So I have to go through the nodes and see where it's running and get the container logs. The correct way of doing this would be this one here.
OK, thank you.
Good.
Thanks for the talk, first of all. Can you share again?
I'll repeat.
Okay. Can you share again the Git repository so we can take the URL?
Of course.
And just, okay, thank you very much. Just mainly that.
So the Git repository is Kalipetis, which is my username, and then swarm-demo.
Thank you very much.
Good. I will also share the presentation later on Twitter, so if you need anything, it will be there. Maybe I will also fix the issue about the port and push an update. We're good? Okay. Thanks for coming. If you don't have any questions, you can also grab them later. I have some Docker stickers if you want. So I didn't have many back home, so just grab me here and I'll give you one. And I hope I can see you also tomorrow morning. Well, we'll see how you can start developing nice applications and then end up in deploying them to a nice cluster. But developing application is a completely different story where we will discuss first thing tomorrow. So get some coffee to the other room, and I'll see you there, hopefully. Thanks again.